All right, welcome. In this video, I'm going to introduce us to non-deterministic finite automata. So as a quick review, let's remind ourselves that a deterministic finite automata, the ones that we've been working with thus far, we call these deterministic because one of the rules that we stated is that for every state, there must be exactly one transition that leaves the state for every character in our alphabet. This is what makes the machines deterministic, meaning that there will be only or exactly one path or one computation that we follow when we process a string W. So this is what we mean by deterministic. There's only one outcome from the input. In a non-deterministic finite automata, we changed that rule. So now there can be 0 or more transitions leaving any state for each character from the alphabet. So first we want to consider, well, what happens if there are no transitions there? Well, this is sort of thought of as just being a shorthand. It's very common in some of the machines we've been designing so far to create a single state that is a reject state that you cannot escape from, that has a self loop with all of the characters from the alphabet. We've been calling these a trap state or a limbo state or something like this. Well, in non-deterministic finite automata, we just leave these states out and we don't have any transitions towards these states. We just assume any missing transition goes to one of these states that forces you to reject. Then we also have to consider what happens if there's more than a single transition. If there's more than a single transition, then we imagine that the machine, the automata, simulates all the possible paths that it could be on all at the same time. So there's a few ways that we can imagine this. We can imagine this being in multiple states at the same time. That's usually how I envision it. Or we can think of it as trying each one of these paths one at a time until it finds one that works. And the way that this plays out in our definitions of acceptance is that if any of these paths lead to an accepting state, then we say that we accept. So that's sort of the idea that if the non-deterministic machine sort of gets a chance to choose between one path or the other, it will always choose the path that leads to the accept state if it can. Now, only if all of the paths lead to rejecting states, then do we reject, because if any single one leads to an accepting state, then we would accept. So another kind of transition that can be added in a non-deterministic finite automata is called an epsilon transition. Now remember, epsilon means the empty string, so we might call these an empty string transition as well, which is a transition that can be followed without consuming any characters from the input. So normally in our deterministic finite automata, we move from one state to another by processing exactly one symbol of the input. This allows us to move from one state to another without consuming any characters from the input. So let's take a look at a simple example, one that we maybe have done before. So this is the language all strings W, all binary strings W, such that W contains the substring 0, 1, 1, 0. And when we solve this with a deterministic finite automata, we designed this machine here. Now remember, the core of this machine is, okay, 0, 1, 1, 0. We can see the substring that we're looking for is what causes us to transition through our series of states from 0 to 4. But then you can see we have all these backtracking arrows that tell us what to do if we don't see the string that we're looking for. With a non-deterministic finite automata, we can make a much simpler machine where what you can see is we still have that 0, 1, 1, 0, but there's lots of missing transitions here. We don't have all those backtracking transitions. Instead, because they're missing, we assume all those transitions lead to reject states. But now what we can notice is that our first state here has a self loop of 0, 1. That means we can stay in state 0 and process the entire string if we want. But what this is really saying to us in our non-deterministic design is saying, well, you can keep processing zeros and ones until you arrive at the substring that we're looking at. Once you get to that substring, remember, a non-deterministic finite automata will take the path that leads to the accept state if it exists. So if that substring truly exists, we can process all the first symbols in state 0. Then when we get to the substring, we just follow it along, 0, 1, 1, 0. Since it is the substring, we will reach all the way to the fourth state, and then any remaining symbols will keep us there. The only way we won't reach the fourth state in this machine is if the substring 0, 1, 1, 0 does not exist at all in our string, in our input string. If it didn't exist, then we can imagine we might start going down this path. We might even get a 0, 1, 1, but since 0, 1, 1, 0 does not exist, no matter when we start going down this path, we will eventually reach a transition that does not exist, and we will reach that rejecting state. The only way we reach the accepting state is if we indeed see 0, 1, 1, 0 in that order to make sure that we can transition to the fourth state. So that's the idea here, is that the non-deterministic machines give us a little bit more freedom. They make a slightly more complicated machine, as we can see here in terms of its processing. But when we actually draw it and write down its transitions and even sit down to think about it and design it, it's actually going to be easier for us to design. So that's one of the reasons why we like a non-deterministic finite automata. So this raises a question that's somewhat central to this series of videos, which is, well, which model of computation is more powerful? We now have our first example of, well, two different models of computation, the deterministic finite automata and the non-deterministic finite automata. And we can think of all the languages that we could make DFAs for. And then we can think of all the languages that we could make NFAs for. And here I've got sort of a set theoretic Venn diagram here. And we can ask our question, how do these two sets relate to one another? The way they're drawn right now, that shows that they're exclusive from each other. I don't think that's probably not the case. There's probably languages that we could make a DFA for and make an NFA for. In fact, if we think very carefully about our two models, we'll notice that every DFA already counts as an NFA. According to how we've sort of said what an NFA is, a non-deterministic one, it has more powers than a DFA. A DFA already counts as an NFA. So that means if every DFA is an NFA, then that means every language that we could solve with a DFA is obviously also a language we could solve with an NFA. So we get this relationship between the two sets. The language of the DFAs is a subset of the language of the NFAs. So another way of saying that is our deterministic finite automata can be no more powerful than NFAs. They can be the same power, maybe, but they can't be more powerful because every single DFA is an NFA. So that leads us to this question. If we can find a language here in this part of the diagram that can be solved by an NFA, but it cannot be solved by a DFA, then that would be sufficient to show that the NFAs are more powerful. We would say NFA is a more powerful model of computation. It can do more things. It can solve more languages. However, that's not the only possibility. The other possibility is that they might have equal power. That's if we can show that for any NFA, any non-deterministic finite automata, that we can create a corresponding DFA such that they have the same language. Then we will say that that means that we've shown that D simulates N. We say that the deterministic finite automata that we created, D, simulates the non-deterministic finite automata, N. So now remember, the non-deterministic one has the extra powers. It can use epsilon transitions, 0 or more transitions. The DFA is more restricted. It has to have exactly one transition for every state and character. And because of that greater restriction in this simulation, in this process where we change one machine into the other, we're going to have to grapple with the fact that in non-deterministic case we have these more powers that we do not have in the DFA case. Now, as I say here, sort of small, this, spoiler alert, this is the case. It is true that DFAs and NFAs have equal power. There are no languages that an NFA can solve that a DFA could not. But why we like our NFAs is because it maybe makes drawing the machine, designing the machine a little bit easier on us when we're sitting down to design them. Okay, so let's start with this very, somewhat simple NFA that I've designed here. And I kind of designed it fairly arbitrarily. I just made some states and made some transitions and just labeled them with some labels and made sure that it was non-deterministic. And, what language this actually solves is not as important as the fact that we can hopefully use this as an example to show how we can simulate this NFA using a DFA. So let's get started with this machine. Now here I've got the NFA version. Okay, we might call it N. And what we want to do is build a DFA. And the way we're going to do this is we're going to try and simulate, that's really, as I mentioned, we're going to simulate the NFA, and we're going to keep track of what states it's in our DFA as we go. So the DFA is trying to do the exact same thing as our NFA, one step at a time. So I'm going to start out by saying, okay, what state do we start in our NFA? Well, we start in state 0, and I want to be careful here and see, are there any epsilon transitions leaving this state? Because if there was, what that means is when we start out, we might be in more than one state. But it turns out here there's no epsilon transitions, so I'm just going to be careful and confident here. I'm going to write a state that just says 0 because I'm going to start in state 0. Now what I'm going to do is I'm going to look at the transitions leaving state 0, and I'm going to keep track. What states can I arrive at if I follow that particular symbol? Now remember, keeping in mind, we only have two symbols. Our alphabet, sigma, is equal to the binary alphabet. So with the 0, what state can I be in? And I just look at my NFA and I follow the transition. I say if I follow 0, I'm back in 0. So down here, I'm going to go and say, well, if I'm in 0 and I get a 0, I'm back in 0. Okay, that was an easy one. What about the 1? Now we see there's actually two transitions here leaving with a 1. And I usually have a little bit of scratch on my side here. If I follow a 1 leaving state 0, I could be in state 0 again. I could follow this one and be back in state 0 again. But I could also be in state 1. So keeping some notes here, I could also be in state 1. Now, what we should also notice is I'm keeping track of a sort of set of states that I could be in here. I could be in state 0, I could be in state 1. I want to make sure there's none others. So I'm going to look for epsilon transitions. Out of state 0, we already looked, there are no epsilon transitions. But out of state 1, there is an epsilon transition, meaning without processing any more symbols, I can move from state 1 to state 2. So technically, after processing that 1, I could either be in state 0, or I could be in state 1, or I could be in state 2. So I'm going to make a new state over here. I'm going to call it 0, 1, 2. It's going to represent this set. And it's going to be if I get a 1, I'm now in technically 3 states at the same time, 0, 1, and 2. And I want to keep track of all 3 states of those. Now that I'm here, 0, 1, 2, I want to go and check, well, what state could I be in if I got another 0? And to do that, I have to look at all 3 states that I'm in. I'm in state 0, I'm in state 1, and I'm in state 2. Okay, now let's check. If I was in state 0 and I got a 0, I would still be in state 0. Okay, check. If I was in state 1 and I got a 0, ooh, that goes nowhere. That goes to the dead state, okay? And so I'm going to say, okay, that branch died off. That if I had been in state 1 and then I got a 0, that branch dies off. However, if I was in state 2, which I could be, and I get a 0, I would be in state 3. So it's possible, after getting a 0 here, that I'm in state 0 or 3. I'm going to label this one 0, 3 for that set. Now, here's one thing I'll notice. Since 3 is an accept state up here, 0, 3 should be an accept state down here. This is saying I could be in state 0 or state 3. If I'm in state 3, I should accept. So if I can get here and I've been simulating, then I should accept, because I could be in state 3. I might be in state 0, but I could be in state 3, and if I'm in any state that's accepting, I should accept. Okay, we aren't done with our state 0, 1, 2. We only figured out where it's going to go if it gets a 0. So let's figure out where it's going to go if we get a 1. So if we're in state 0 and we get a 1, oh, I should be up at this machine, and I get a 1, I could be in state 0, I could be in state 1, or I could be in state 2. We already did that one before, so we know that this set at least, maybe more, but at least this set, if I get a 1 from 0, I will still be in that set. Now if I get a 1 from 1, where am I going to be? I'm going to be in 2, which is already in my set, so I don't need to add it back in there. And if I was in state 2 and I got a 1, where would I be? According to this machine, that's a dead one, so there's no other states I need to add here. So it looks like the only states I could be in are 0, 1, and 2. So again, let's be careful here. If I got a 1 here, I would be in state 0, 1, 2 again. Okay, we're almost done. Remember, for our DFA to be done, we need a 0, 1, 0, 1. It's only this last one here, 0, 1. Okay, so if I'm in state 0 or 3, and I get a 0, let's see what happens. If I'm in state 0 or 3, and I get a 0, what happens? Well, if I'm in state 0 and I get a 0, I'm at 0 again. So keeping track, I'm at 0. If I'm in state 3, wait a second, state 3 up here has no exiting transitions. So if I get a 0 from this one, I die off. There's nowhere place for me to go. So if I get a 0 from the state 0 or 3, since the path in 3 died off, the only path I have is this one. 0 goes back to 0. Okay, what about 1? We'll do our last one now. If I'm in state 0 and I get a 1, we've done this a few times now. I know I can get a 1 and go back to 0. I can get a 1 and go to 1, and then I can follow the epsilon and go to 2. So I'm back into this state again, 0, 1, 2, 3, or 0, 1, 2, sorry. That's if I got a 1. But if I'm from 3, again, there's no exiting transition. So if I get a 1, there are no other states I should add. So it looks like if I get a 1 here, I just go back to this state, 0, 1, 2. Okay, so now double checking, I've now added that 0, 1 on the last state. There are no other states that we needed to add. Maybe I would have had to add one for one of these ones, but I didn't after doing my analysis. So we're done. This machine here is now D. And because of the strategy we took to make sure that it simulates N, it's doing the exact same thing N does. It's in the same states that N is. We know that the language of D is equal to the language of N, at least informally. We haven't formally proven that, but if you followed along the steps and you kind of believe that those steps, that we followed them correctly, then you probably believe that indeed this is a corresponding machine or a simulating machine. So returning to the slides, if we go and we check the machine that we designed, indeed this is the same machine that we just designed by hand. Okay, so again, we can simulate that NFA by creating a DFA. Now notice, we did this for an arbitrary NFA. I just kind of made it up, meaning we should be able to apply the steps that we followed to any NFA that we have, and in that process create any DFA. And we're going to have to formalize that in a second, but before we can formalize that, and by formalize I mean write a proof, we need to say what an NFA rather is in a more formal sense. So to do that, let's take a look at our formal definition of a non-deterministic finite automata, and let's remind ourselves that this is very similar to our definition from the previous video of a deterministic finite automata. The only difference here is we're going to change a little bit of the rules. So let's just review some of the different sets. Now, first of all, remember a DFA was a 5-tuple, and NFA is also going to be a 5-tuple. All that means is a collection of 5 things. And the 5 things here, we gave them names: Q, sigma, delta, Q naught, and F. And then here we're just sort of saying what these are. Some of these are going to be exactly the same as the DFA. Q is a finite set of states, same as the DFA. We might have different states in the NFA than the DFA, but we're still just a state machine with a finite number of states. Same thing, we still just process symbols of an alphabet. So there is some alphabet here. That's a set of symbols. Nothing's changed there, okay? I'll also mention that I'm going to skip over delta here for a second, but for Q naught, that's still just a start state. So there's just some there's just some state selected out of the set of states that is our start state. And then also there is some subset of states that are our accepting states. All of these are the same. The only thing that's really changed here is our rules about 3, the transition function, in the non-deterministic finite automata. And maybe this part makes sense because in the finite automata, we said there has to be exactly one transition for every state and symbol pair. Well, that's not what we're saying anymore. We've changed two things here. One, we changed sigma to sigma epsilon. What does that mean? There's a little note here at the bottom. Note, sigma epsilon is just sigma with the empty string added in. So all this is saying is the transitions that we have now, not only do they have transitions for our alphabet symbols like 0 and 1, for instance, they also have transitions potentially labeled with the epsilon symbol or the empty string. Okay, great. So this bit says you're allowed to have empty string transitions. But remember, the other change we made said that you're allowed to have 0 or more transitions for any state character pair. Well, before in our old definition here, we said that this function went to Q. We mapped from a state and a symbol to a new state. But now, what does this say? P of Q. This means the power set of Q. And if you remember from set theory, what is a power set? A power set is the set of all subsets of Q. So what this is saying is we map from a state and a character to a potential subset of states or set of states. Okay, and it's going to be important in our when we simulate a DFA with an NFA that, or sorry, other way around, NFA with a DFA, that we're going to create a single state for every subset of states. And we saw that in our little example there. We had states labeled 0, 1, 2, or 0, 3. Those were labels of subsets of the original states. Okay, so that's what we're seeing here. So this definition doesn't change much other than re-specifying delta R transition function to be more permissive, allowing more types of transitions, epsilon transitions, and then 0 or more transitions for any one particular state character pair. All right, let's take a look here. This is a formal proof. It's not fully, I haven't got all of the parts of it, but all of the parts that are maybe important for us. We're going to try and formally prove now that if you have any non-deterministic finite automata n, and then you can build some DFA D that has the same language. So if there's some language that's the language of an NFA, then that language is also the language of a DFA for some DFA D. What we're going to do, we're going to use what's called a proof by construction, where we are going to construct the DFA that corresponds to n, and that's going to constitute our proof. Just like we did in our example, the only difference is in our example we used a specific NFA. Now we're going to use a general NFA so that our proof is general. Okay, and what does that mean? So when we say we're going to start with the general NFA, that's this first sentence here. Let n be some formally defined NFA. So we've got a Q, we've got a sigma, we've got our delta, our Q naught, and our F. That fully defines our NFA. Then we give a heads up to our readers. What are we going to do? We are going to make a new machine, a DFA D, and it's going to be different. And even though our definitions of DFAs are very similar to NFAs in the sense that we still have a set of states, we still have an alphabet, and so on, we want to make sure that it's clear to our readers that what we're doing here is we're making a new machine. So we're going to give new names. I'm going to say Q prime. That's hinting that we're probably not using the same Q. Notice I did not use sigma prime. Now why not? Because what we are saying here explicitly is the alphabet for my new machine is the same alphabet for my old machine. I'm not making any changes to sigma. That doesn't make sense. But all of our other potential parts of the 5 tuple might change. New set of states, new transition function, that part makes sense. Maybe a new start state, okay, and maybe a new set of final states, okay? So all of those might have to be new, all right? Now, to get started, we do need one little piece of formalism that's going to help us out. So let's start by assuming we have some set of states R that is a subset of Q. Now those are our original states in our non-deterministic finite automata. So we've got some subset. Now what does that mean? Well, when we were drawing our pictures, one of those subsets R might have been 0, 1, 2. The set of all states 0, 1, and 2. That was one of the subsets that we were in. Another one we had was 0, 3. Okay, but it could also just be a set with a single state in it, like the set containing 0. Okay, whatever it is, let's just think of R as being a subset of states. Now we're going to define this new set here, E of R. Okay, it's going to be all the states Q that can be reached from R by traveling along 0 or more epsilon arrows. So if we are in the state R, but some of those states in the state R have epsilon transitions leading to other states, we want to include those other states into this set, E of R. Okay, so E of R is all the states that we can reach from R by possibly following some epsilon transitions. Okay, now remember in our original example, one of our states did have an epsilon transition, and it was important for us to follow that transition after following other transitions to keep track of all the possible states we might be in. And that's all that E of R is doing here, is it's helping us say, okay, after maybe we make a transition, let's follow the epsilon transitions to see all the possible states we could reach. Okay, now all I have down below here is a definite, this is going to be how we build D from N. So we need to be careful here. Let's start out first. What is our set of states going to be? Well, our set of states in the DFA, we need to have one set for every possible combination of states we could be in the NFA. Remember, the NFA, we can go into all these weird combinations depending on how the machine is set up, and we want to be able to keep track of any of those combinations. So we're going to make one state for every state or set of states in the power set, or subset of states perhaps. Okay, now notice in the example that we did, that didn't end up happening. We did not make every possible state. That's because a lot of those states were unreachable in the machine we were looking at, and that was by design. I didn't want to make a very big DFA in my example, so I designed one that would have a small corresponding DFA. However, in practice, this step could be very large. Why? The power set is exponential in size of the original set, meaning if our original set had n states, like 10, then our new power set of states is going to have 2 to the n states, or 1024 states. So we could go from an NFA with 10 states to a DFA with 1024 states. So because of that, this is one of the reasons why we like NFAs. We can be way more efficient with our NFAs than we can be with DFAs. Sometimes it's just better to design NFAs to avoid this exponential explosion or growth. Now, we don't typically build DFAs this way. If we were doing this, it might be not by hand. We would be doing this maybe in a machine. And if we were doing that in the machine, we would accept, okay, we might have this exponential explosion in the number of states. If we were going to do this by hand, we would probably say that exponential explosion in the number of states is enough to make me not want to do it. If I have a 10-state NFA and I need to convert it into a 1,000-state DFA, that's going to take too much time, and I probably don't want to do that. So we're doing this here as a formalism to explain that we can do it, to prove that we can do it, so that we can show the language of NFA is the same as the language of the DFA. But again, we might not actually go through these steps because they're a bit burdensome. Okay, so let's keep going. Now, what we'll notice here is we're now saying that out of our set Q prime, we're not going to call them Q's anymore. Those were the states in our original subset. We're now going to call them R because these correspond to subsets of our original set of states. Okay, so in the DFA now, where any state is always going to be a subset of the original states. Okay, and now we're going to also process some symbols. So maybe we're in that set R, and we're going to process this symbol A, and we want to know where should we end up? Where in our transition function should we be? So what we're going to do is, the first thing we're going to do here, let's just look at this little bit here. This bit says, take the state the states are that we're in, okay, and see where you would end up if you processed A. So let's imagine one of the states in our set was state 0. So what this is saying is, well, first go look up in the original machine and see where would you end up if you were in state 0 and process the A. Now let's imagine in our set R there were another state, maybe state 2. Then we would go and we would also do this again for state 2. Where would I arrive if I process an A from state 2? And then, any states in R, we would do this for every single state in R that exists. Now, after we figured out which states we could arrive by processing the A from our sets R, then we're going to use this E definition saying, well, now go and follow the epsilon transitions too. So we followed all of the transitions for A. Now from that set, we will follow all the transitions with epsilon. And all of those states, all of those original states from the original set Q that we might be able to reach from processing the symbol we've processed and by processing the epsilon transitions, all of those states become or characterize our new set of states that we might be in. So this is just telling us how we can link up when we're in set R and we're processing an A. How do we find that new set, R prime maybe, of states that we might be in? And again, just simply we process the symbol from all those states and then we process the epsilon transitions as well. That's really the clunky bit. That's the hard bit, okay, because we have to do this for all subsets R. Then we just have a little bit of final touches, cleaning up that we need to do. First of all, where is our start state? Which one is our start state? Well, we need to be very careful here. Our start state should be the same as the start state of our original machine, but we need to keep in mind there could be epsilon transitions leaving that start state, and that might reach other states. So our start state of the DFA might be more than just one state from the original set of states. In our example, it was just 0, but in other examples, it might not be. So we need to make sure we remember to put this E set here, where we follow the epsilon transitions and then make that our start state. And then I mentioned this in our example. When we are looking for our final states, we just look for any set of states that contain one of our final states. Okay, so for our R, which is our set of our new states, if R contains one of the Q's, which was in the original final states, then R must be in our new final state. So that's just making sure that any of our states that could be potentially accepting states are now labeled as accepting states, and this completes our proof. Okay, now usually to kind of follow through with this proof and understand what it's doing, we need to do that example. Luckily, we did that example to start out, hopefully, adding some understanding to this proof here. But what this proof allows us to do is show that the set of languages accepted by NFAs is the same as the set of languages accepted by DFAs, meaning that these two models of computation are of equivalent power. They do the same thing. They can solve the same languages. Now, what that means is we can conclude this discussion with a redefinition, if you like, of the set of regular languages. So in an earlier video, we said a language L is regular, or is called a regular language, if it corresponds to, or if it's equal to the language of some machine where that machine is a deterministic finite automata. Well, now we can redefine that using non-deterministic finite automata instead, saying effectively, if you can make a non-deterministic finite automata or a deterministic finite automata for any language, then that language is regular. So this gives us sort of two tools now in our toolkit. If we want to prove a language is regular, we can either build a DFA for it, but if that seems like a little bit hard for us, we can design an NFA for it as well. All right, thanks a lot for watching. We'll see you in that next video.